This is a short tutorial that will show you how to represent chemical energy, ECH, in three ways. The first way is using a balanced chemical equation with the energy term as a reactant or a product. The second way is to show chemical energy changes using an energy diagram, comparing the energy content of the reactants to the products. And the third way is using energy bar charts to show how chemical energy changes throughout a chemical reaction, in addition to thermal energy and phase energy. Let's take a look at our first chemical reaction. This is the decomposition of baking soda. Recall in lab that for this reaction to occur, it was necessary to supply energy continuously. Because energy is being absorbed into the system from the surroundings, we call this an endothermic reaction. We can represent this symbolically with a balanced chemical equation where energy is a reactant since it was supplied to the reactants to start the reaction. We can also take a look at the energy changes throughout this reaction. Because energy was supplied, that tells us that the initial reactants are low in energy. They have low chemical energy. And because energy is conserved in a chemical reaction, that energy is now stored in the products, and the energy content of the products is now much higher. Let's take a look at this decomposition of baking soda reaction in greater detail. We can do so with energy bar charts. Energy bar charts allow us to visualize what might be going on at the atomic level during certain reactions. Let's take a look to see how energy content is changing in an endothermic process. Before you draw your energy bar charts, it is a good idea to first write out the chemical equation. Since this is an endothermic reaction, energy is a reactant, so we write energy on the left side of the equation. In this reaction, the chemical energy of the system is increasing. Specifically, the energy content of the product is higher than the energy content of the reactants. This is because energy is being absorbed into the system from the surroundings. To show this increase in chemical energy, we will draw fewer bars in the initial panel under ECH and additional bars in the final panel under ECH. Note that it's completely arbitrary how many bars you draw. In this particular example, I've drawn 2 bars for the initial state and 4 bars for the final state. Next, you will consider thermal energy. We can assume that this reaction starts at room temperature by drawing 2 bars under ETH in the initial panel. We can also assume that after the reaction is complete, the system is going to return to normal temperature or room temperature. We will show this by drawing 2 bars again in the final state under ETH. To keep things simple, we will ignore EPH or phase energy. Comparing the initial state of the system with the final state of the system, we can see that the final state has more energy compared to the initial state. Specifically, there are 6 bars in the final state and only 4 bars in the initial state. Since energy is always conserved in a chemical reaction, we need to show conservation of energy by drawing additional bars in the energy flow part of the energy diagram. We will show 2 bars of energy going into the system from the surroundings by heating, represented by the letter Q. But hold on a minute. How does energy transferred by heating, Q, wind up making the chemical energy of the system go up? Chemical energy has to do with the rearrangement of atoms during chemical processes, whereas thermal energy has to do with the motion of particles. Isn't heating dealing with motion? This is puzzling. How does energy transferred by heating make the molecules rearrange themselves in this chemical reaction? To answer this question, we have to zoom into our system and look at the behavior of atoms at the particle level. Atoms are always moving around. In order for a rearrangement of atoms to take place, and this is necessary for a chemical reaction, energetic collisions between the reactant particles are necessary. Low energy collisions do not bring about rearrangement of atoms. In order to bring about sufficiently energetic collisions, we have to heat up the system. Heating up the system will cause the thermal energy of the system to increase. This increase in thermal energy will allow for more higher energy collisions between particles. Therefore, the increase in chemical energy that we saw in this reaction has to come from a decrease in thermal energy. Let's see how we can show this visually using our energy bar charts. At the very start, the reactants were at room temperature. Again, here we're showing 2 bars under thermal energy, ETH. energy was added into the system. The energy that was added from the surroundings into the system goes directly into our thermal energy account. We can show this with an increase in thermal energy under hot reactants. Notice that chemical energy remains at 2 bars, since there's no direct change in chemical energy yet. Now that our system has a sufficient amount of thermal energy, the reactant molecules can collide and rearrange to form product molecules. We can show this in our energy bar chart with an internal transfer of energy from our thermal energy account into our chemical energy account. Notice here that 2 bars from ETH are transferred into the ECH panel. The 2 bars initially came from the surroundings by heating.